Hey guys, so this week I'm going to be talking a little bit about glycolysis and delta G, and then finish up with giving you guys a breakdown of the pyruvate dehydrogenase complex. So I'm starting with this glycolysis and delta G concept, and what this is kind of based on is all of these pathways that you're going to learn in this class. They all feed into another reaction. So anytime your body does a reaction where you're starting with some amount of enzyme and substrate, and you eventually produce a product here, this product immediately gets fed into another step of your pathway. And the reason for this is that you have these reactions which are based on your delta G. And the basic principle behind how our bodies work is that the delta G for all of these reactions has to be negative. The reason for that is if they're not negative, essentially they stop working. So when they're negative, they're spontaneous, and essentially when you're eating something, you're able to continually digest and metabolize it because all of your reactions are able to occur spontaneously. So what happens is if that doesn't happen, and say this gets blocked here, you start building up a large amount of your product, and I'm actually going to add product to this part of this equation here, and that's going to mess with your delta G, and it's going to no longer be in this negative state, and it's going to switch to a positive state. And that's what happens a lot of times when people get various sicknesses where their pathways are functionally broken at some point. So if you look at this table 16.1 here, it gives you a list of delta G double or delta G naught and also delta G. And if you look down the delta G category, you can see that almost all of them are listed as negative. If you read the caption, it says that not all concentrations are completely known, which is why you may see that this one and this one are slightly positive, but they speculate that those are just inaccuracies in the calculating metabolite concentrations. So the overall principle is that you really need to maintain this negative delta G at all times. And in order to do that, you need the next reaction in your cycle to work. Okay, I'm going to talk about this pyruvate dehydrogenase complex because I think it's not well structured in your guys' book. So the pyruvate dehydrogenase complex has two main cofactors. Really it has four cofactors, but two of them that get used actively, and then two of them which are just used for regeneration. So when you look at this thiamine pyrophosphate, or TPP, oh, the terrible looking P's. TPP here, pretend like I can actually draw something well. The only part that you actually care about is this guy that I'm circling in green here. The rest of it is just structural things for holding it within the protein. Same thing with this lipoic acid. This here, we only care about this SS bond here, which we are going to use to do redox chemistry. Okay, so the first step is we're going to take this TPP and using a base within the enzyme active site, we're going to pull off this proton here. And that's going to give us a negative charge. And this now anionic TPP here. From here, this is going to interact with a molecule of pyruvate. And what's going to happen is you're going to have spontaneous decarboxylation. So we're going to lose this carboxyl group. And I'll come back to the TPP portion of it in a second. This can pick up a proton to form an aldehyde, which is a fantastic electrophile for our TPP up here. So this can come in, do a nucleophilic attack, and we'll get, gonna grab another proton from this also. Oops. Nope, not that now. And I'm going to draw the pyruvate portion of it in red now, so you guys can see. Where that came from. So let me erase. Where's the big guy? Some of this. I'm just going to draw this part of it in red, but you get the point that the whole thing would be right here. Okay. From this point, we are now, so we've now generated this TPP, which has an acetyl attached to it. Whoops, okay. Sorry, I was supposed to do a separate one for the decarboxylation, but I just did that, so we're going to lose this. I'll go through it again, just so you guys have it. Grabs a proton. This will come in and attack, pick up a second proton on the oxygen, and we'll get that should be R. This molecule here. Okay, so from this point, we are now interacting with a thiol here. So this is going to pump 2 electrons in, and we're going to generate, let's see. So this guy is going to grab here. We're going to make an anion at this position. I'm going to switch back to just black. Plus R. This is going to start to get tight at the top of this page. Lipoic acid now. Okay, so our lipoic acid is going to do what's called, it's going to be an oxidation. So what's going to happen is we're going to end up donating electrons from this bond here, And we're going to end up with this product from our oxidation, which looks like minus and I'm going to go back to drawing the pyruvate portion of it in red. So we had 2 electrons from this OH, which ended up protonating here, making our double bond. Now we have a whole lot of electrons, so they have to get dumped somewhere, and they're going to get dumped. 2 of them are going to get dumped down into here, and the other 2 are going to get dumped into this sulfur complex here. And that gives us our negative, which is shown here, and this lipoic acid complex. So from this point, we've actually regenerated our original anionic TPP. So we no longer need to do that first step where you pulled off the proton that was here. After you do that once, you no longer have to do it in the cycle because it just keeps happening during this phase. Our last step is a displacement with coenzyme A. So this is going to come in, act as a nucleophile to this thioester here. And this will give us acetyl-CoA plus lipoic acid, or dihydrolipoic acid. So from here, we're now going to have to oxidize this back up to lipoic acid, but we've generated our product already. So in the first 3 steps here, we generated our acetyl-CoA end goal, and now we're just trying to regenerate the enzyme. So FAD is being used as an oxidant. So with FAD, picking up the 2 protons and reforming this bond here, we will generate our lipoic acid back, plus FAD H2 plus, no, not plus, H2. And then the final step is that NAD plus, so I'm going to redraw this over here, can pick up the protons from this FADH plus, giving us back our FAD, and giving us an NADH equivalent, plus a proton here. And as you guys will find out, this goes on to make more ATP. We've successfully regenerated our lipoic acid and our FAD within this process. So this citric acid cycle, this pyruvate dehydrogenase complex gives us both a molecule of NADH as well as a molecule of acetyl-CoA. Okay, that is all for this mini lecture. I hope this was helpful for you guys. If you have any questions, please send me an email.